Good morning, everyone. I'm Alex. I work in a company called Brium that does a lot of ML stuff, sometimes compilers, not always. And in case you don't know how EuroLLVM and LLVM meeting keynotes work, you usually submit a talk. And then the program committee loves it so much, they reach out to you and say, hey, Alex, how about you do a keynote instead? And looking at your faces, I understand that this deep dive into MLIR to LLVM, whatever, is kind of boring talk for an opening keynote. So I'm not going to talk exactly about that. I'm more going to tell you a story about how MLIR and LLVM connect, how they come to be in that connection historically, and what we can do in the future. We will do a deep dive for maybe 10, 15 minutes. That's what's about the amount of time I was planning to talk for. But we're also going to talk more about keynote stuff, about MLIR, LLVM, and what can you do with them. So there are many ways to interpret this connection or integration. So certainly MLIR is part of the broader LLVM project. So are many other sub-projects or libraries in LLVM. We can also say MLIR is sort of a spiritual successor of LLVM. LLVM itself, we can think of it as sort of static single assignment form with useful instructions and type. And it's really useful. It has been around for like 20 plus years. And a lot of people are using it happily. MLIR took that and tried to generalize it, sometimes overgeneralize it if you ask me, but it's SSA with regions and a way to bring your own instruction type. So instead of LLVM having, here are your addition operations, here are your floating point numbers, please send us an RFC if you want to add a float. In MLIR, you don't need any of that. You can just go and add your types, your operations, your attributes, etc. It's not an introduction talk to MLIR. I'm going to assume most people are somewhat familiar with it, so that's as much of introduction of MLIR as I have on my slides. And finally, more technical parts that I originally intended to talk about is that we have a bidirectional translation between MLIR representation and LLVM IR. It's a technical presentation, we'll get into that, and it's basically a way to connect one project to another into one complete compilation flow. Before I can talk about the connection and basically to justify why the connection works the way it works, I need to tell you the origin story of MLIR. So MLIR was sort of created out of realization that a lot of the work these days in computer science goes into machine learning or what people call artificial intelligence. And back in the day in 2018, TensorFlow was kind of the most popular ML framework at Google as well as outside. And a team at Google was looking at it and saying, well, you know, if you kind of open the TensorFlow black box, the way it works, it's almost compilers. It's like full of tiny little cute dragons there. I know LLVM love dragons, so TensorFlow is also a compiler thing, except it was not using a proper compiler design. Or maybe it was. It was and is actually using a compiler design, just not an LLVM style design. So a team at Google led by Chris set out to fix that and provide a compiler infrastructure that would support both things like LLVM IR and abstractions like the ones used inside the TensorFlow ecosystem. So it started in early 2018. It was pushed to the TensorFlow repository first and stayed there. So it was pushed in April 2019 and stayed there for several months before we proposed it to the LLVM Foundation to be upstreamed into the LLVM project. It took several months to negotiate what the exact criteria is, but it was finally merged in tree around December 2019. So there is some time that we spent in a small team, and then there is some time that we spent in a different project with slightly different contribution rules, building out MLIR before it was contributed wholesale without additional review. Maybe we should have reviewed it more. One more important thing, yes, I left this space there to say, well, yes, that's an important event I missed. I joined in late 2018. I've seen most of MLIR. Many people think I've been around all the time. I haven't. And that's what I've seen as state of the project in late 2018. Well, there was an IR folder with lots of things. Just to give you an example, if you know MLIR, you know it has like operations and nothing else. It had 7 or 8 different concepts back in the day. It had some analysis like normal SSA dominance. It had first-class support for polyhedral. I come from polyhedral compilation world. I was super happy about that. It had 17 operations, most of which were borrowed from LLVM. Well, it had actually more in TensorFlow, but the MLIR project by itself had only 17. And it had some useful transformations like canonicalizer, which is equivalent of inst combine, vectorizer, some loop transforms. Do you know what it didn't have? Any way to execute this code. You can transform it, you have IR come out, and you're happy. You can not do anything with just IR other than read. So I sort of set out to fix that by making sure MLIR connects to LLVM, so we can then use LLVM compilers to produce binaries that we can run and understand that our transformation actually makes sense. They make program fast while keeping it correct. So that's what I did over that year, mostly in private repos. So we take TensorFlow, we converted to this beautiful polyhedral representation. We converted to a normal control flow graph. If you see in a compiler IR, it is usually a control flow graph. Well, except that it didn't have branches in MLIR, so I had to add them. Then we convert that to LLVM IR. Well, we translate MLIR to the equivalent in LLVM. Well, except MLIR operations kind of transparently worked on tensors, which are these like big multi-element objects. So we kind of had to go back from an add on tensors to affine loops and to CFGs and again, and go back and have sort of a loop in the lowering process. Kind of ugly. And then we can call, for example, org.jit if you run from TensorFlow, or just emit LLVM IR called clang or LLC. Except we had this type called memref for member reference, and it had no ABI, so we had to define it. So there was a lot of work, and a lot of this was doing what you would normally do, writing an LLVM compiler. So you write a lot of code using the LLVM IR builder to produce LLVM IR before you can invoke passes and all the useful things. And we didn't quite want to do that because MLIR, if you don't know or assume it stands for machine learning IR, it's not. It stands for multi-level IR. And going from a loop directly to LLVM IR is what Clang does. There is not much multi-leveling in there. So at some point we decided, yeah, we should probably do this LLVM dialect. We've been talking about dialects for months as sets of individual operations. So LLVM dialect was one of the first that was added as sort of intermediate layer between all the other MLIR instructions and the LLVM IR world. You go to that thing, then you can go to LLVM. Many of the things still exist. They set up the foundation for what MLIR codebase is today. So this polyhedral to CFG translation is now called convert SCF to CF. CF is control flow, S is structured. CFG conversion to the LLVM dialect is called convert whatever. We now have like a dozen dialects to LLVM, both of which resulted in the so-called dialect conversion infrastructure. LLVM dialect to LLVM IR resulted in a thing called module translation. There is an execution engine in MLIR that sort of abstracts away the way the LLVM execution engine works. The polyhedral and LLVM together resulted in the generalization to having only operations with regions, as we do right now. And LLVM dialect was the first one to introduce custom types in MLIR, so you can now bring custom types. So if you used MLIR, you recognize these things. These things are still there. A lot of the code we sort of wrote in late 2018, 2019 is still there. It's probably one of the heaviest exercised code in MLIR. And we are kind of in this situation that I borrowed. So all of the MLIR and ML infrastructure built on it is somehow relying on the code a couple of junior-ish engineers wrote as essentially hobby project. I'll tell you a secret. I was never on the official MLIR team. I was a random researcher in Google Brain, and I liked compilers. It was this cool thing going on, so I started contributing. And now I'm sort of unofficial maintainer of the thing. So just to give you slight more amount of details on the LLVM dialect, the design objective of that was to mirror LLVM IR as closely as possible inside MLIR abstractions. And as a result of that, the translation from the LLVM dialect to LLVM IR should have been as straightforward as possible. Some examples, if you have an operation in LLVM, which is on the right, in MLIR it will have the same, just with prefix with LLVM dot, that's the dialect, and it will have a slightly different syntax, but basically if you know one, you can read the other pretty much easily. Same for calls. Then interesting stuff starts. At some point, MLIR sort of thought, well, we have some people who have been working on LLVM for many years, and we kind of think there are some design mistakes, maybe not, but suboptimal design in LLVM IR. So how about we fix that? One of that was phi nodes. Phi nodes are great. They're a canonical way of representing data flow along control flow edges in SSA forms. But there is a better way. There is a way that's called functional, where you can have basic blocks with arguments. That's what MLIR has. Except that when you have these, you can actually branch to the same block with different values, which you cannot do in a canonical SSA form with phi nodes. So translation gets a bit ugly now that one conditional branch requires you to create a new block. Another thing we can highlight in MLIR, we really cared about multi-threading the compiler. So things like going to a global context or a global register of things were considered bad. So for example, we have constants as operations in the IR and not a special class of value. We generally wanted to generalize, so we don't have a special class of value for anything, just value. So basic blocks are not values. And we also generalized metadata to what we call attributes. It's a sort of structured, well-defined, verified metadata on each operation. So for example, a no inline metadata can be on function, and we have verification rules that says, well, this metadata is existing or not, but you cannot say no inline equals 42. That just doesn't make sense. So now we generalize that to having functions as operations, not first-class entities. But what we needed to do is sort of mirror LLVM IR into MLIR and be as close as possible. And then translation is simple. We don't want to write yet another huge LLVM IR emitter. And then the translation is really simple. It's in pseudo Python here, but it's really mostly English. So for each function, we first translate signature, and then for each global, we kind of do the same. And then we do the same for certain kinds of metadata. We understand its attributes. And then for each function, for each block in that function, we are going to just create a new block, convert all operations except for the terminator, and then connect the terminators using the phi nodes in LLVM. It's really straightforward. Like if you understand both projects as how you would write it, it was really maybe 200 lines of code when it was initially contributed. That was good. So we could take MLIR in almost any form, translate it to lots and lots of LLVM IR, feed that to Clang or LLC or whatever it takes that LLVM can use, and then run it. We can run it, execute, and then live happily ever after. It's a story about dragons. Until we sort of realized these things exist. They're called GPUs, and people really like them, especially in the AI world. They want to run stuff on them. And not only that specific one, but that, and there are some things called accelerators and TPUs, and we have to support them somehow. So the way LLVM deals with it is LLVM has platform-specific intrinsics, and we thought it was an error to separate instructions from intrinsics, so we decided to push on the dialect idea. And now we have a dialect that's specific for NVIDIA GPUs, and another one that's specific for AMD GPUs. And all of those are sort of borrowing intrinsics, which themselves are borrowing from the ISA of the corresponding hardware, and we have many of these. I didn't do the stats. I only counted operations in the biggest ones. So AMD and NVIDIA GPUs by themselves contribute 300 operations that we need to handle. CPUs are slightly more reasonable. There is like 50 in the two dialects I looked at. There's more. Like if you look at all of them, there's probably 1,000, if not more, operations that we need to reason about and translate. So we looked at this, and like I don't really want to write a 10,000 or 20,000 lines of code file with a huge switch that says, oh, if I see an NVIDIA intrinsic, emit this intrinsic instead. And by the time we had this glorious feature of MLIR called interfaces. If you don't know what interfaces are, but do know object-oriented programming, then you know what interfaces are in MLIR. They're exactly what their name suggests in object-oriented programming. Which means you can say in MLIR, hey, operation, are you translatable to LLVM? If so, please translate yourself. And that's how it works these ways. This interface, I'm going to show you a bit of code, and trust me, I'm going to get back to cute dragons after that. It's really what I said it is. So it's a way for, well, a dialect in this case, to tell how to convert operations from the LLVM dialect, or actually any other dialect in MLIR, to LLVM IR. It takes an operation, it takes an LLVM IR builder. If you ever wrote code using LLVM IR, you probably know that object. And it has a module translation, which is basically a way to store information between different invocations of this interface. It has another thing called amend operation. It comes from this realization with GPUs that a lot of them are using sort of weird metadata, and it might belong to a dialect that's different. We have an LLVM operation with an NVVM, which is NVIDIA stuff, annotation on it, saying, oh, here it's a kernel, or I know that this operation is the one producing your thread index, so it never exceeds 1024 or something like that. So sometimes we need to amend an operation after we translate it based on a different interface. That's pretty much it. That's all you need to do if you want to support a new dialect in the LLVM translation. You basically need to implement that interface on your dialect. That's it. There are 2 functions, or 3 actually. I'll show you the 3rd one. But that's pretty much all you have to do and it will work. So it takes an operation. It takes the set of instructions that are produced, and then you can modify them. There is the same set of mappings between that we can use. There is last one, convert parameter utter. That's like metadata on function arguments. It's a bit special. We will look into that. And it also doesn't make a lot of sense to have it, but we do. So now we could take MLIR, convert it to lots and lots of LLVM IR, feed it into Clang, and run it on a GPU. We looked at that, and we decided, yeah, we could live happily ever after. Until we realized that OpenMP is a thing, and our first major adopter in LLVM upstream was the Fortran compiler Flang, and apparently they really, really care about OpenMP in the Fortran world. And also some people working in our team were into these polyhedral compilations. They also like OpenMP and sort of automated parallelization. So we looked into that, and yeah, well, MLIR likes dialects. Everything is a dialect. We can have an OpenMP dialect. Except that when we want to translate that to LLVM, it becomes ugly. If you haven't seen OpenMP inside LLVM, well, that's kind of location information. We can ignore it. Don't really ignore it in your code. It's really useful. But for the sake of the presentation, you don't have to. What OpenMP does, it has a runtime library. And it does lots of calls to that runtime library. So your code that comes from the left is actually getting outlined into a function that's getting called by the runtime function. It's nice design. It's a bit ugly to handle when you write a compiler, because for MLIR, you have to think about regions, outlining, globals. You have to know how the MLIR runtime library works. Luckily for us, there was this thing called OpenMP IR Builder. It's now called OpenMP Frontend. That has like 22K lines of code, and we didn't really want to rewrite that, so we decided, how about we reuse that? So we modified our module translation object to just return an instance of an OpenMP IR builder and call it. We also had to expose the possibility to convert individual blocks. Before, LLVM has functions, and functions have blocks in them. How hard can it be? Now, suddenly, in the model we need to convert it differently for OpenMP blocks than we do for normal dialect blocks. And we also needed to reconnect phi nodes after that because of the difference we've seen. And because OpenMP is this nested thing and so is MLIR, they're both modeled in this nested way, so we can have nested loops. Well, that's normal. We can also have nested parallel constructs. If you write OpenMP code in any language, you can have pragma OpenMP parallel inside another parallel. We can have multiple work shares, and we just mirror them in MLIR with this infinitely nesting region structure. So we sort of had to add a stack object to translation. So we have a virtual stack the translation code can use. So we have stack frames. If you've seen LLVM code, it roughly follows what LLVM does with the CRTP pattern. So there's a stack frame. There's a thing you can derive. So for example, we have an OpenMP loop information stack frame in which we can put any information that the OpenMP builder needs to build loops. It's just code. It's reasonably well documented. So we did that. We could run this translation using the infrastructure we built, converting OpenMP to MLIR. I think it's probably the last code slide I have. I'm not sure. I'm trying to get through the code. In that module translation object, we have a way to save the state of translation to push it onto a stack, and then we can walk that stack looking specifically for a certain kind of the operation. So if you remember the slide, we can mix multiple kinds of regions, each of which can have its own kind of stack frame. And then we might only want to walk through loop stack frames. Or because MLIR allows you to mix dialects, you could have OpenMP regions mixed with, I don't know, normal loops, mixed with lambda functions, mixed with something else. And you probably don't want to reason about stack frames from the dialect you're not a part of. So with that, we could take MLIR, we could translate it to lots and lots of LLVM IR, we could run it through Clang with libopenmp and run it on multiple CPUs, and we were happy and decided we could live happily ever after. Yeah, you see where I'm going with this. There is a thing called OpenACC that didn't even have a logo I could use, so I just put some text, and we looked at that. And we actually didn't have to do anything. It was supported by the functionality we've had added already, and we were happy. So just to summarize the technical part of it about translation, if you want to go to the LLVM IR from any MLIR dialect, what you have to do is implement this little interface called LLVM translation dialect interface. It's very consistent. You translate to LLVM. It's a dialect. You have an interface. Any implementation in this can use an object called module translation. That object contains the intermediate mapping, so if you go from MLIR value to LLVM value, you can ask. Also the other way around, if you go from MLIR function to LLVM function, you can ask. That's where it's all stored. Also gives you some possibility to translate individual blocks, types, attributes, and so on. You can trigger translation recursively because MLIR itself has recursive structure. And one thing you cannot do, you cannot have custom types. Well, that's kind of a design choice because LLVM IR itself has a fixed type system. MLIR does not, but it does not make sense to also build a type conversion infrastructure for that. That's pretty much the technical deep dive. Now we can step back and reflect a bit. So we have this code. It's really simple. Is it general enough? Well, in MLIR, everything is an operation. We can convert operations, so it kind of is. Another question is, why do these things exist? Why do we translate globals separately and functions separately? In LLVM IR, it makes sense. Globals are its own thing. Functions are their own thing. In MLIR, they're all operations. Why can't my translate operation handle that? Same here in the interface. I talked about this convert parameter utter. Why cannot we just use the amend operation on the function operation? It's a good question. So I started digging into that, and I found this old commit of mine that introduces this convert functions logic and the entire flow. It's not huge. The date you see on the slide is actually wrong. It's the date when all the commits that we had internally were pushed into the TensorFlow repo. Somehow it's split between March 29 and March 30, but all of those happened before. It's like likely December, November 2018. And it says lower scalar parts of CFG functions to LLVM IR. Just to give you an idea how old it is. Does somebody in the audience know what a CFG function in MLIR is? Or has seen the distinction between CFG and ML functions? No. Meaning, even that justification that I wrote, and I cut it short. That justification is a third of what's actually written in the commit description. Makes no sense anymore unless you have historic context for how MLIR evolved. So this added these convert functions, which made sense at the time. And then this commit 5 years later was adding support for something called grid constant by a person from NVIDIA because they needed it. And they decided to add this convert parameter attribute because functions have parameters and you can put attributes on them. That's kind of metadata that we really want to convert when we go to NVIDIA. And yes, that person actually checked that their first and only commit to LLVM. They could not have known this thing I know about CFG functions and why this logic with convert function and loop exists. You know who should have known? Probably the senior person reviewing and approving that patch. As you can see, it was me. And I approved it because I forgot about it in the spirit of the moment. I thought about this presentation and was preparing for this being a keynote, I thought, well, I am going to show you a proof that a lot of the code in LLVM dialect and in translation between MLIR and LLVM is old and we should revisit it. So I did some stats. And the code is not actually old. Most of the code was touched last year or 2 years ago, and we're on track to touch it more. It's a naive way of looking at it. I tried several less naive ways. So I looked at commits. I tried to filter out the NFC non-functional commits. I tried to filter out documentation and typo fixes. And all of those were still showing that most of the code in the translation is relatively new. What isn't is the design. So what I want to say here is a lot of design decisions in MLIR, especially parts that were added early in the project, may have made some sense at the time when we made the decisions and may not have make sense anymore. Yet we keep adhering to those decisions. We keep using this convert function. We have a function called translate module to LLVM IR. You know why? Because module was a separate thing and we want to translate a module. We also have the inverse. We have translate LLVM IR to module, which, like, why it's called that way? Just for symmetry. And that is not a new observation. It's not specific about MLIR or LLVM or any programming community. There is this story on the internet called the monkey ladder experiment. The story pretends it's based on science. I have actually found no evidence that there was an actual experiment conducted like that, and by the description, it doesn't look like a scientific experiment. I went even further. I found a friend of a friend of a friend who is an experimental psychologist. In their training, they actually work with monkeys, and she told me there is no such thing as a monkey ladder experiment. But I think it's a useful metaphor. If you don't know, the experiment is allegedly going as such. 5 monkeys are being put into a room. They're being fed and taken care of, and everybody's nice to them. And in the room, there's a ladder. And on top of the ladder, there are bananas. At some point, one of the monkeys will try to climb the ladder, grab the bananas. And if it does, it triggers a cold shower, so everybody gets showered with cold water. At some point, monkeys realize that, we are good here, we have food, who cares about those bananas? Let's just not climb to avoid getting doused with cold water. And then one of the monkeys gets replaced with a new monkey. And the remaining monkeys will prevent the new monkey from climbing up the ladder because they don't want to be showered with cold water. The process continues until all of the monkeys are replaced. So at some point, none of the monkeys have experienced the cold water, but they all somehow know not to climb the ladder to get the bananas. That shows what one may call tradition or institutional knowledge. There are actually papers on a similar thing called the cargo cult, and there is a lot of that in some of the early MLIR design. So I think we should not be like those monkeys. We should not be just people who follow whatever is established because it's established without trying to understand. So I would like everyone in MLIR and in the broader LLVM and generally in the broader software ecosystem to take maybe 5% more time to try to understand the rationale behind certain design decisions. Maybe there was not even a conscious decision. Maybe it was something that was easier to do at the time. And really does not take a lot of time. Do a git blame, do a git log. I made those slides in maybe 5 minutes. I spent much more time going through the code and doing code reviews. You can check forums, you can check mailing lists, you can ask around. You can probably find a person who was around when the decision was made and can give you some historic context. And one thing that's important, I've seen this too much time, but assume good intention. If you don't know, assume people actually knew what they were doing and don't come and say, oh, it's all wrong, we should fix everything. It's an easy one. If you want a harder one, we should probably document design decisions better. Stands for MLIR, stands for LLVM, pretty much everything. We have a great community, great tooling. We post these RFCs. I love RFC discussions. I know some people hate them, especially around MLIR. They tend to get long. Sometimes we get like several hundreds of comments that you need to get through to understand what's going on. What we don't usually get is some sort of summary. So to understand why a certain design was adopted, you need to read through pages and pages and pages of great technical argument. But it's unclear in the end what decision was made and why. So how about we write that? It also will take you 10 minutes as a patch author to say, well, the discussion reference this, kind of summarize the discussion and say, well, we decided. Maybe we should also consider putting accepted RFCs into Git or have some sort of single persistency. Forums are great. Sometimes it's hard to jump between forums, old mailing lists, commit information, documentation. MLIR used to have this rationale document. It was last really updated in 2020. We should fix that. And then a harder one. Sometimes we need to challenge legacy design decisions that no longer make sense. First, again, I'll repeat that we must acknowledge that this decision most likely made sense when it was made. But then we can think that maybe it doesn't anymore. Propose a better one. I also understand and I see, well, I don't really see there's like light in my eyes, but I know some people, especially in the industry, are not very happy with how LLVM and MLIR tend to change sort of fast over time. But it's part of the evolution. We should not confuse the stability aspect of LLVM for immobility. We want to be able to change, we want to be able to improve, we want to be able to learn and use those learnings in our projects. To mitigate that, we can devise a clear migration strategy. There are several good efforts. I think, I don't remember how many years it took to introduce opaque pointers, but in the end, we managed to have opaque pointers in LLVM. It's a good design decision, and there were lots of discussions and some tools to help migrate all of the infrastructure, the test, and so on, from the old representation to the new one. We can think about it. We shouldn't be stopped from revising design decisions that we think no longer make sense. And it might be easy for me to stand here and ask every single one of you to do extra work, so I'll start with myself. This is me. Yeah, if you don't recognize me from my picture, maybe this will help. So I do a lot of forum communication and chats and whatnot, and I think that's my second most common phrase in MLIR discourse. If you want to translate to LLVM IR from MLIR, you must go through the LLVM IR dialect, and we must keep the translation simple. And I was thinking about this, and I say this a lot, and some people are not really happy about me saying that, and they actually make sense there. So the simplicity of the translation is the corollary of the original design goal for the LLVM dialect. To reflect LLVM IR, a corollary, the translation should be simple. Except that now we are not only translating the LLVM dialect, we are translating like a dozen of related dialects, some of which are modeling intrinsics, some of which are modeling a completely different programming model like OpenMP or OpenACC. We have a technical translation system which uses like recursive blocks and this stack and so on, and interfaces and dynamic dispatch and lots of stuff. Is it really simple anymore? So maybe we should rephrase that and say dialect to LLVM IR translation should be pay only for what you use. And yes, that means we should remove the dependency on libopenmp frontend or make it optional. So going back from that to the overall MLIR design, maybe there is a new corollary to make. We might need a new dialect if we are going to do something with it. Just introducing a dialect for the sake of it being a dialect, while it was great for pushing MLIR forward, today, do we want to add to the complexity of the thing? Yeah, maybe not. So when thinking about this, one way I think about this is to think about transformations. Are we going to do something with this IR? And then we can do a trade-off, we can balance. So we know from a keynote, I think 2 years ago by Mehdi and Jeff, that MLIR manipulation is on average 3-4 times slower than that of LLVM IR. And adding more dialects to MLIR increases the cost for everyone. There is compile time cost. Obviously, there is also some runtime cost because sometimes you need to go through all of the operations, all the types you have. And then there is the cognitive cost. orienting yourself in the MLIR infrastructure is hard. I used to do this big graph you might have seen on slides before on how dialects in MLIR relate. I stopped because I cannot keep track anymore. There's like 50 dialects that we have. So adding more dialects is costly. However, if you have dialects, you have explicit operations that are like normal instructions, you can reason about that, you can query them, you can transform them. It's arguably a better API than just transforming intrinsics. Transforms and analysis in MLIR, most of them are designed to work through interfaces. So when you add a new dialect, you can say, well, I have an operation. It does not have side effects. It does not have something else. It's speculatable. So your common sampling special elimination will just work out of the box by writing 2 lines. You don't have to change the pass. You don't have to change the analysis. One thing that we were really proud of when we designed MLIR is MLIR context and the general ecosystem supports multi-threading in the compiler in general. So MLIR context object is thread safe. And it means we can sort of offset that 3-4x slower manipulation by this manipulation being concurrent. So there is something there that we can trade off for simplicity. We used to push for more dialects as sort of forcing factor for MLIR development. It's been 6 years. I think it's enough of forcing MLIR development. We can stop adding dialect just because we think it's a good contribution. We need to add them because we can add something useful to the broader ecosystem, to downstream projects, to other projects like Clang or Flang. So before adding a new dialect, especially a dialect translatable to LLVM IR, we might wait whether it is worth to add this dialect or not. If not, then it's perfectly fine, and I know I said the opposite many times, but now I think it's perfectly fine to take whatever dialect you have. If that's where you stop your transformations, you can take that and go to LLVM IR using the infrastructure we already have. One controversial thing I'll say from the stage just because I can is, well, we have this arithmetic dialect and math dialect and several others. They're basically a carbon copy of LLVM IR, except they also support arithmetic contenders. Maybe by this criterion, we should get rid of those. Maybe we should just have an LLVM dialect and use that, or have an arith dialect and not have an LLVM dialect. I don't know. Somebody please start an RC. So I might have veered off topic a bit. I'll conclude with where I started. MLIR is a part of a broader LLVM project along with many other good projects. I think in MLIR, in LLVM, we should be more aware of our design decisions. We need to take effort to understand them. We need to take even better effort to document them. Actually, part of the reason why I'm standing here is I realize I have not documented a lot of the decisions I have made. So I'm trying to fix it by coming here and presenting them and have guys in the back record me doing so there is a record. And then some of the decisions can and have to be challenged. I showed the way, it's for the others to do, but please remain friendly. We don't want a discussion that goes into a shouting match. We can challenge decisions, but just assume that everybody who made the decisions had thought about it. By doing so, I think the LLVM and MLIR integration will be better than any technical content I might have presented today. Thank you. Any questions? Yes, there are mics. I think you can come to the mics.
Hi. So is it true that every conversion from one IR, from one dialect into another dialect, causes a performance penalty? And if that's true, what's your estimate?
Performance penalty in compile time or runtime?
In runtime, execution time.
I don't think it does. I think it's the opposite. So there are two things. There is conversion between dialects. And generally, the idea of conversions, they are not an optimization. They're just going from one abstraction to another. But going to another abstraction is a way to enable certain transformations. For example, you go from structured loops to control flow, and then you can do CFG simplification on that. That creates a CFG that's not reducible to loops, for example. So normally, the conversion itself should be roughly nothing, like a no-op in terms of runtime, and then you can do further optimizations. If you can't, then you should probably not convert.
I have a question about RFCs specifically. Looking back at an RFC, which is a discourse thread with hundreds of comments, can be time-consuming and frustrating. Is there any interest in the community in formalizing the RFC process and making it kind of a first-class citizen that gets, an RFC has, undergoes review and gets committed just like code does?
Yes, so I'm not speaking for the community. There are some discussions in the newly formed LLVM Project Council on, we have started thinking about that. We do not know what the answer is, and I think it's great to have a process to give some structure, but we also don't want to put unnecessary friction in that. I know a lot of people complained about MLIR RFCs taking a long time. So there is a balance to be found, but I would say there is a general interest in somehow structuring these discussions and making sure we keep track of them. For example, for the LLVM project, we now commit accepted RFCs on specifically governance into a Git repo. We might eventually do the same for LLVM, but it's a discussion to be had as an RFC.
Okay, thank you.
Hey, Alex, the numbers that you spoke about on the Git log, the increasing of the changes on the translation side, do they include only from MLIR to the LLVM side or the other import side as well?
Yeah, only export.
Okay.
Import is newer.
Okay, so thanks.
Thanks, Alex. I think this is a good time because once more and more code base builds on assumptions, and then it's harder to change because the amount of change that would be required will be enormous. And even if you have a better design in mind, it will be hard. I mean, people have limited time and stuff. The second part question really I had was we could draw some parallels with LLVM, which has a longer history. And in your opinion, okay, how much of that LLVM design changed 5 years, 7 years into LLVM? Probably LLVM was so well designed that there was no need for change.
Yeah, of course, it's perfect. It's been perfect since day one, except that we keep adding operations and keep changing the type system. Some design decisions can be revised and should be revised later. And sometimes new things come out after the initial design. I have not looked at LLVM evolution in the first 5 years of LLVM. I was probably in school at the time. If somebody here knows the answer.
I mean, one thing I can think of is maybe the scalable vector part, which much later on for the SOE. And there were optimizers, somebody down the road made the middle optimizers better, but those are really add-on. They don't really change fundamentally the intrinsic design, the architecture.
Yeah, I generally think of LLVM and MLIR as sort of these deep stacked systems, and there are some things that are very core to the systems that are extremely hard to change. Should we replace SSA with something else? Maybe at some point we'll have a good argument, but it is going to be extremely difficult to do so. And there are some things that are easier to change, like adding a new type, like adding new floating point types is the recent addition, or scalable vectors. So there are some things that are very fundamental to the design, and there are some other things that might be easier to change, and we should weight the complexity of the change and the cost for other projects in the ecosystem against the benefit of the change. Okay.
Thank you.
Which Johannes goes first? I'll start. I know the one thing that scares some new players away from MLIR is the sort of extreme diversity of the dialects and the volatility of them, that they change all the time, new added. There's sort of no concept of a standard set of dialects. And I think that has also been discussed a few times. And as far as I understand, we don't want that. But can you sort of comment on the balance between having some concept of a stable standard that's maybe even versioned versus, as Jeff New phrases it, embracing the chaos?
Yes, so just for historical context, we used to have a standard dialect, and I removed it because I didn't want to sit on the standards committee. But no, the real reason is it was very high stakes discussion to add something to the standard dialect because it's the standard. So I think what we should do is better document the state of a dialect. So when you start something, you can document, well, I just started. It's gonna take me some time to figure it out correctly. Please come and contribute. It's one extreme. Another extreme is like LLVM. LLVM is very stable or as stable as LLVM IR gets. So please don't change this unless you have a really, really good reason, which means LLVM IR changed. And there is a spectrum in between. And the problem is we just don't know where each of the dialect lies on that spectrum. And that's a matter of documentation. It's easy to fix. Like, let's open laptops and fix it right now. I think it's the last question.
Great. Thanks for the talk, first of all. It was great. So to follow up on an earlier question, it's like you gave a talk about MLIR to LLVM IR translation, like a deep dive into this. What parts do you think LLVM IR should adopt from MLIR to maybe make that translation easier, or just because it was a good design in MLIR that we should adopt it just because?
There are two things that I find interesting. One is some sort of API support for intrinsics that's better than what we currently have. Like have a function and the function call and resolve by name and just magically know that this specific function call means something. Well, I think we had the discussion before and you can kind of build most of MLIR out of intrinsics. Another part is regions. I don't exactly know how to model regions in LLVM IR. There have been a keynote, I think, I forgot, several editions ago on convergence infrastructures that had some ideas. We had discussions about loop regions and loop passes in LLVM for ages. So some concept of a region, so like a multi-block set of IR that's sub-function, I think that might be useful for reasoning and for isolation and transformations.
Okay, cool. Thank you.
Okay, that's all I have. Thank you, everyone.